So we're going to start by talking about bijective functions. So we're going to start with the definition. We're going to say that a function f from a to b is called bijective, or another phrase that's used is a one-to-one correspondence. If it is both one-to-one and onto. So remember we talked about one-to-one and onto last week. So let's suppose that I'm working with finite sets. So let A and B be finite sets. And let's say I have a function f from A to B that's a bijection, or a bijective function. Well, since f is onto, and these are finite sets, we know that the number of elements of B has to be less than or equal to the number of elements of A, but also because f is one-to-one, we know that the number of elements of A is less than or equal to the number of elements of B. And so if you put these two facts together right here, this one and this one, we learn this means that the number of elements of A and the number of elements of B are exactly the same. So let's kind of summarize this. So I'll just call this a summary of what we just did. We learned that if f is bijective and A and B are finite sets, then they have to have the same number of elements. A and B have to have the same number of elements. And so you might ask kind of the converse of this statement. What if I start out with sets that have finite sets that have the same number of elements? Is there a bijection between them? So if A and B are finite sets that have the same number of elements, so the number of elements of A equals the number of elements of B, then there exists a bijective function f from A to B. So in fact, the converse is true. And let's look at an example here to demonstrate that. So let's consider two sets that have three elements in them. So A is going to be ABC, and B is going to be the set X, Y, and Z. And they both have three elements in them. And so we want to create a bijection between them. You can kind of see this in terms of picturing this function you want to make, A, B, and C, X, Y, and Z. So to create a bijection, I have to send each element from the left over to one element on the right, and they all need to go to different ones. So for example, I can send A to X, b to y, and c to z. That will be a one-to-one and onto function. So bijective functions from a to b are, I could send a to x, b to y, and c to z, but that's not my only option. I could have sent instead a to y, b to z, and c to x. That's F2. F3, I could send a to z, b to x, and c to y. And then if I go back here to this one, I could still send a to y, but instead b could go to x and c could go to z. If I go back to this one, I could send a to z, but then b could go to y and c could go to x, or go back to my first one and I would still send a to x, but now I'm going to send b to z and c to y. So in total, this list of 6 functions here, these are all the bijective functions from a to b. So in total, there are 6 bijective functions from a to b. And so if you kind of connect the 6 to this number that we started with, how many elements did we have in each set? We had 3. 6 is 3 factorial. So you might ask, is this true for any number of elements? So that's this theorem 10.7, which says if A and B are finite sets with the number of elements of A equal to the number of elements of B, which is n, there are n factorial bijective, I'll say then, there are n factorial bijective functions from A to B. Now I'm not going to go over the proof in detail. The proof is in your book, but let's think about it in the case of our previous example. So let's think about why this is true here. Here's A, here's B, right? We had A, B, C, and you had X, Y, and Z. So let's start with our first element, A. There are 3 different elements that I could send A to. I could send A to X, A to Y, or A to Z. So there are 3 options. And then once I've chosen a place for A to go, then B has 1 less option. So when I'm looking at this B, there are 2 options for B to go to, but then once I send, so for example, if I send A here and B here, then C has no option left. It has to go to the one remaining if I want it to be a bijection, so C has only 1 option, or really no option. And then we multiply these together. So we get 3 times 2 times 1, or n factorial. And so you can extrapolate and see that this is true in general. You would just have more than 3 elements. you would have n elements.